Let's get back to how to calculate limits, and specifically how we can use the squeeze theorem to obtain some limits. That's method number 6. You'll find this material in section 3.7.6. The squeeze theorem, you'll probably be applying it a lot if you're trying to calculate the limit of a trigonometric function. You can't do it any other way, but it can be useful to determine other kinds of limits, and it's quite a nice theorem. But before, let's motivate why we would need something called a squeeze theorem. Let's say you want to calculate this limit. Now, based on the things we know, we could apply the product rule, which by the way only works if the individual limits exist. And this is where we run into a problem. This limit exists, it goes to 0, but this part is actually meaningless. That is because when x goes to 0, the inner part of the sign goes to infinity, and sine of infinity has no meaning. So we do have a problem here. How can we solve it? Now, from your perhaps mathematical intuition or plugging it to Wolfram Alpha or your preferred tool, you will see that while sine 1 over x squared is actually varying between +1 and -1, quicker and quicker and quicker as x goes to 0, x squared is going to 0. So these amplitudes become smaller and smaller, and this actually goes to 0. Now in Physics 101, it's not just about getting the right answer. If that was the case, we would be done. Mathematical intuition would be all you need. Here we also want to have mathematical rigor, something you can demonstrate why this is 0, and not just because you can see it in your head. Let's have a look at the squeeze theorem, how it is defined and how you can use it. The squeeze theorem, in a very general way, is used to try to calculate a limit when we can't, but where we can find functions that are actually bracketing the behavior, the local behavior of the function at that point. An example graphically that we can think of, let's say that we have this weird curve and we want to calculate the limit at this point. And for some reason, just assume it and go along with it, for some reason we can't really calculate it analytically for this f of x. Now, a way to try to do this is if we can find two functions, say g of x and h of x, that bracket the function at that point, we can actually use them to calculate this limit. So a practical example could be thinking about a function g of x that does something like this. Let's call this g of x. And another function, h of x, that brackets the function from this side. Now if we have functions defined this way, and this is a completely arbitrary example, that's really weird, and I had to amend it multiple times because this was no longer a function, because x was actually returning different values of y, which means it would not be a function at all. But just go along with it. The point is that if you can find functions g of x, h of x that bracket it in the vicinity of the point, and it means that very close to that point you will be able to write a condition such as this. Or in other words, you need to find functions that in the vicinity of the point you want to calculate the limit for obey this condition. If it's just higher and lower, then you're going to get into trouble because the squeeze theorem is not really going to work. And the point about the squeeze theorem is if you're trying to find a given value, but you can't, you can try to look at functions that bracket it and that essentially basically touch it at the point or the vicinity of the point. And if you understand these two functions, you can take the limits and you want to be in a condition where those limits will be the same, and if they are the same, it means the limit at the point of f of x is that value. But let's define it explicitly. Now the squeeze theorem says that if you want to find the limit when x goes to a point A of f of x, and you can't really find it, but you can find functions where in the vicinity of x of a this holds, and if you can know or find the limit when x goes to a of g of x, and if this equals L, as in your lecture notes to be consistent, and if the limit when x goes to a of h of x is also L, if these three conditions hold, the squeeze theorem tells you that this limit is also equal to L. And a nice way to look at this is if in the vicinity of x equals a this holds true, you can also take the limits of the three expressions or functions which will retain the conditions. So let's try to do this. Taking limit when x goes to a of g of x is lower or equal than the limit when x goes to a of f of x, which is lower or equal than the limit when x goes to a of h of x. Now in the squeeze theorem, if you know that these values are the same, this means this is L, this is L. The only way to maintain these conditions, this is higher or equal, lower or equal, is for them to be equal, which implies that this has to be L as well. Now in practice, using the squeeze theorem can be very complicated if you need to come up with the equations for the functions, or as in the next example, it can be quite easy if you actually start from your knowledge of the functions you're looking at, and then you transform it to get to g of x and h of x. And sometimes you may even be doing it without realizing it, but it's very good to understand the formality. And also when we look at fundamental limits, for example, sine x over x when x goes to 0, the squeeze theorem is actually a very neat way to prove that such limit is actually 1, but we'll get there. Well, now that we know the basics of the squeeze theorem, let's try to solve this. But before, let's not even think about the squeeze theorem, and perhaps then realize that we have just applied it. One thing that we can think of is this component. Let's just think about what it's doing. And if you know anything about trigonometric functions, you will know that the sine, and let's just say a variable z, and let's say that z in this case is 1 over x squared. We know that sine will vary between +1 and -1. Right? This is the basics sine. Whatever thing you plug in, it can never be lower than -1, it can never be higher than +1. Now one thing that we can do, and in many cases to solve these limits that is possible, is can we have a look at the expression and see how we can transform it to look like this. So the first thing we can do is come back with this variable change. We said this for any general z, but this is also true for 1 over x squared. In a mathematical rigorous way, this is only true provided that x never equals 0, which is fine because we'll go for a limit. What we can then do is, if we look at this expression and the one we want to calculate the limit for, the only difference is x squared. So why not just multiplying x squared everywhere, so we maintain the balance and we make things look much more like the original expression. So this gives us minus x squared as lower or equal than x squared sine of 1 over x squared which is lower or equal than x squared. So the only thing that we've done here is we've multiplied by x squared. Obviously you need to multiply everywhere, and if you don't, you're breaking the condition. So this will no longer hold. Now the great thing about this is if you have some sort of relation, you can always take the limits. So you can take the limits in the same way that you'd be multiplying everywhere. You can take the limits everywhere and the equalities or relations will still hold. So this means that by taking the limits, we can write that the limit when x goes to 0 of minus x squared is lower or equal than the limit when x goes to 0 of x squared sine 1 over x squared, which is lower or equal than the limit when x goes to 0 of x squared. If you reach to this point, then this becomes quite straightforward. The reason for it is we don't really know. I mean, we know this is 0 because we can think about it, but in general, we might not know what this limit is. And the great thing about bracketing it with functions where we can calculate the limit very easily is that we know, in this case, we know that this is 0, and we also know that this is 0. So the only way that the relation can hold, so this is higher or equal, and this is lower or equal. If there's 0 on both parts, it implies that this is 0. This is how you show in a mathematically rigorous way that this limit is 0. How is this using the squeeze theorem? That's a really good question. Now this is using the squeeze theorem, but in a way that we didn't even have to think a lot about it. So I started with something that you already knew, that the sign can vary between -1 and 1. And all we did was we converted the expression so that in the middle we have exactly the limit we want to solve. Now in the process we have actually came up with functions that we could call, for example, g of x and h of x that are bracketing f of x. So actually, and because these limits exist and these functions do bracket this one because it follows from here, we are in the conditions of the squeeze theorem. And this is actually a very nice application of the squeeze theorem, even if you're not thinking about the formality of it and defining what is g of x, what is h of x, and f of x, and the limits existing, and so on. So it means that this method, number 6, using the squeeze theorem, doesn't have to be all about formality actually. It's really just about understanding that specifically for trigonometric functions, they will vary between specific values. And if you can start with this condition and then transform it, you will solve a lot of limits. In other cases, and I'll try to show some more complicated ones, this is really not possible. And you actually need to come up with functions g of x and h of x that bracket the function. But we'll get to there in another video.